Let's continue and finish this chapter. There's just one more proposition to do and the chapter is over. We go to chapter 3. Sumitra, did you start recording?
Yes.
Yeah, it's really something.
I think you can click on participants and there I think you can see that.
Okay, well, I used to hear that, I don't hear anymore. Anyhow, let's finish this section. We saw that G, the Gramian is always positive, so it gives us a kernel function. So we can produce an RKHS out of this. And now we want to explore more and see what is this H of G. We know it exists and what is it. And here is the proposition. And when you sit and do this little by little, it's not something difficult. It becomes a triviality at the end. But still, it's good because with this, with almost linearity, we'll see it's conjugate linear at the end. Any Hilbert space can be looked as an RKHS. So not to mix H with the Hilbert space that we are starting with, let's call it L. So L is a Hilbert space. With inner product that I will denote by L. And define K by define K on L. Note that L here plays the role of X. In other words, the point of the space are L, element of the Hilbert space. See by the formula K of X and Y, two elements of L, defined to be the inner product of X and Y in L. Then we know that it's a kernel function. Then this part we know. Function. Of course, it's better to mention on X equal to L, emphasized our point set is L. And H of K, or as I wrote above, H of G, because the Gramian is positive, but H of K is a better notation, is precisely the vector space of bounded linear functionals on L. In other words, it's the dual. And the norm of a functional as an element of this space in H of K is the same as the norm as a bounded linear functional on L. You see, so we start with K and right here, proof. if we fix some points, say x1 up to xn, well, it's sometimes they write h, sometimes they write. I want to show that k is positive. K is positive is equal because it depends on it's defined on L. It means that for any H1 up to Hn on L, the matrix K, Hi, Hj is positive. That's the meaning, and for any n. And what is this? This is equal to, for any H1 up to Hn in L and for any n, the definition of K K of H1 and Hj. Definition, K of x and y is the inner product of x and y. So this is the inner product of Hi and Hj in L. And this is precisely the Gramian. And we saw this in a previous proposition. The Gramian is positive, therefore K is positive, and we have a kernel. And so we have an RKHS, H, which can be called H of K or H of G if you want. I mean, any of this notation. We have a reproducing kernel Hilbert space whose kernel is K, but note that H is defined, or element of H is an RKHS on L. Its element are functions on L. If F is in H, then F is defined as a function on L. We want to distinguish these functions. What are these? To start with, as in the Moore theorem, we try to see what are elements of W. So what is K, Y? Ky at point X, note that these are elements of L. By definition is K, X and Y. This is the definition of K, the relation between little k and capital K. And the definition of capital K is the inner product of X and Y in L. And this is precisely the inner function, the linear function created by Y at point X. So K of Y is equal to Fy, which belongs to, we can denote it by L star for any Y. And if you do any linear combination, sigma alpha j kj, to obtain what are the elements of W, it's j from 1 to n alpha j f y j. And you need to be careful here. I write it in red. Be careful. This is sum j from 1 to n f of alpha j bar yj. Because yj is on the second component, when the inner product is on the second one, and when you took it inside, it becomes bar. And then it's f of the sum j from 1 up to n alpha j bar yj. So at the end of the day, any combination, if sum fy with y in L. And this shows that W is precisely over L star. Is the family of all bounded linear. And indeed, without explicitly saying that, I use Riesz theorem, because Riesz theorem says that any element of L star is of this form. For any element of L star, there is a y such that the linear functional is of the form fy. So in rather implicitly, Riesz theorem is used here, but at the end, we see that W is equal to L star. And recall the discussion we had with Sheldon before the break. Why can I go from here and say W bar is also equal to L star? And this is, in the finite dimensional case, the same justification work, everything is complete. So we have this. In the infinite dimensional case, here is the way to do it. What is the inner product of fw1 and fw2 in K? What is this? Well, this is equal to by what we have here, the kernel function at point W1, kernel function at point W2 in K. And this is K of W1 at point W2, which we know is capital K at point W2, W1. Again, I write it in red to be careful here. And that, by the original definition of K, is W2 and W1 inner product in L. So the golden formula is that FW1, FW2, their inner product in K is equal to the inner product of W2 and W1 in L. That's the principal identity. And now from this, you have the isometry we are looking for. What is the sum of alpha I if Wi, I from 1 to n, its norm in K? Well, you square it, and I have done this before. I do not repeat this again, but I have done this before. You square it is if the norm with its inner product with itself, one sum with I, the other sum with J. You have this. Then you replace it by this and do the reverse operation in L, and then sum them up. at the end, you find it's the sum I from 1 up to n alpha I bar because of the change of the order here, wi in L squared. For any collection of wi's and alpha i's. So this has some interesting consequences. One of them is what we wanted to prove here, that W bar is equal to L star 2, because if you have any Cauchy sequence here, it gives a Cauchy sequence there. That Cauchy sequence is convergent, and then you go back to the beginning in the original one is also convergent. So this implies that W bar is equal to L star. It's the whole dual. And also we have an isometry. I mean, the isometry that C from L star, which is our h of k to L, it's enough just to say f of W maps to W, because as you saw above, you can put alpha I here inside, it becomes alpha I bar, and then sum and obtain the same thing. It's not indeed something new. I have done this before. So we have this C, and C is an isometry. But it's conjugate, I mean, because of the bar which is there. So this ends the proof, what I wanted to prove. So it shows that because of this surjective isometry, it covers all W. Because of this surjective isometry, instead of looking at L, which is an arbitrary Hilbert space, you can look at L star as an RKHS. So in other words, L is almost L star is almost a copy of L with a better property that it's an RKHS. Why I say almost? Because it's not linear, it's conjugate linear. But still, it's a good way to do it. So in the light of this proposition, even though we saw before that L equal to L2 of 0, 1 is a Hilbert space, but not an RKHS, which is true. But if we look at L star, it's almost equal to L, and this one is an RKHS. That's the content of this section. Well, this is a long journey. This finishes our chapter 2, and now we can start chapter 3. We have about 30 minutes. We can start the very beginning. Indeed, chapter 3, interpolation and approximation, it's mainly on interpolation. That's one of the earlier reasons kernel became important. They have applications in interpolation and sampling and approximation, and the basics are covered in this chapter. Let's start with a definition to see what interpolation means. Definition. Here, X and Y are sets. X1 up to Xn are elements in X. Oh, why it's like that? And it's very important to keep in mind all the time that they are distinct. And y up to yn are element of y, not necessarily distinct. They can be repeated. A function g from x to y such that g of x I is equal to yi is a function that we are looking for. And the technical term that we use, we say that g interpolates these points. Well, I say a function g from x to y, which does the job, but most of the time we have a function space. In our case, is a reproducing kernel Hilbert space H, and what we want G, not any function, G to be in H and interpolates both. This makes the life a bit more difficult, and that's the topic of this section. Another notation which I will frequently use, if I denote this set by f, x1 up to xn in X, and I have a reproducing kernel H on X, the space generated by kernel function kx1, kx2 up to kxn, this will be denoted by H index F. I forgot a span. Put here span. The linear span of kx1, kx2 up to kxn is a finite dimensional space, and will be denoted by H of F. Clearly, the dimension of H of F is less than or equal to n. And now I seek some equivalent condition to see under what conditions this dimension is equal to n, or equivalently is strictly less than n. This is important to arrive at our main theorem, which will be, I believe, next week, because we just have 30 minutes. But we proceed to see how we can do that. Well, first, dimension HF is strictly less than n if and only if. If and only if what? There is alpha 1, alpha n, not all equal to 0, such that alpha 1 kx1 plus alpha 2 kx2 plus alpha n kxn equal to 0. True, that's the meaning of being dependent. And this happens if and only if this happens, if and only if there is alpha 1, alpha n, not all equal to 0, such that for all f in H, F inner product with this equal to 0. In other words, I replaced this identity being equal to 0 by being orthogonal to all elements, in simple fact in the Hilbert space. Something is 0 if and only if it is orthogonal to everything. But now use the fact that we have a reproducing kernel. So there is alpha 1, alpha n, not all equal to 0, such that for all f in H, sum j from 1 to n, alpha j bar, f at point xj equal to 0. So you don't see the kernel anymore, somehow hidden. And this means that there is a relation, a linear relation, non-trivial one, which works for all elements of this space. So how it's written here, well, it's just a formula, but it means that there is non-trivial linear dependence between the elements. Another way to write the same thing is that there is alpha 1 up to alpha n, not all equal to 0, such that for every f in H, the vector f of x1 up to f of xn is orthogonal to the vector alpha 1 up to alpha n. True. And now we obtain another characterization. All of these are equivalent. The first one, I wrote it in red. Let me add, this one is red too, if and only if I define T index capital F from H to Cn by image of F is its trace, F of Xn. This relation says that the range or the trace of this is orthogonal to an element which is not 0. This is equivalent to say that this is not surjective. Surjective. That's another characterization which I will use. Okay, this is good. This is good. Well, there are several of them. I just highlighted 2 of them, dimension less than 1, and the fact that this is not surjective. But sometimes the one in the middle, I will also use that. There is a linear dependence between the elements of H. So in these cases, if this is the case, we see that we cannot interpolate. So here we see that if this is the case, the point, there is no function f such that f of x1 is equal to alpha 1, f of x2 equal to alpha 2, and f of xn equal to alpha n. We cannot interpolate this point alpha 1 up to alpha n as our y1 up to 1j. So this is, if we look at the very beginning, dimension less than or equal to n, up to here, TF is not surjective. We see that this is also equivalent to the fact that we cannot interpolate x1, x2, xn with all of Cn. Another comment is that I have mentioned this comment before. The stuff like this might happen either in this form or in this form, as we saw in examples 1 and 4 at the very beginning. K0 was equal to 0, K1 equal to 0 in one example, and in another one, K0 minus K1 was equal to 0. So a relation like this can happen. Another important observation is that H of F, the finite dimensional space is in H, is automatically closed. So we can talk about the projection on F. Instead of writing projection on H of F, it's simpler to write P of F, but I mean, more complete is P on H of F is the projection, the orthogonal projection onto HF. I will use this. What is the properties of this? G, assume that G is in H. G is orthogonal to F. G is in HF perp, or G is orthogonal to HF. If and only if, because we know is some elements which span this space F, if and only if G is orthogonal to the set Kx1 up to Kxn, because the span of this is equal to HF. And this means that G inner product with Kx1, G inner product with Kxn, all of them equal to 0, and more concisely, G at point x1 is equal to G at point x2 is equal to G at point xn equal to 0. I write this again because this is, even though simple, but it's very important. G is in HF perp if and only if Gx1 equal to 0. Let's see immediately one consequence of this. Suppose that F is an arbitrary element of H. No restriction. So F at point x1 is something, point x2 is another complex number, and so on up to F to xn. And now look at the projection of F. Still is in H, but is in HF. What can we say about this projection? What is PF at point x1 and PF at point xn? Can we say something about this? And here is the point, the meaning of PF is important. PF is the orthogonal projection. So PF is orthogonal projection onto HF. Therefore, for any F, F minus its projection is orthogonal to this space. When you orthogonal into a subspace, the difference is the difference between f and its projection is orthogonal to that subspace. And now use this box formula. If something is orthogonal to h of f, then at all points x1 up to xn is equal to 0. So f minus the projection at x1, at x2, and at xn, all of them are equal to 0. So in other words, pf at point x1 is equal to f at point x1. And pf at point xn is equal to f at point xn. What is the message of this? This is something very important. Message is that if you want to interpolate it really with point x1 up to xn, it really doesn't matter if you stay outside and look at all functions in the space, or go into the smaller finite dimensional space of HF and study the same problem. If, of course, if the answer here is yes, the general question is yes too. And moreover, if here the answer is yes, it means that if you can interpolate some points, then you don't need to stay outside. You go inside and still there is a function which does the job. And that function is better by this proposition. If you want to go for minimum energy or minimum norm, let x1 up to xn be a set of distinct points in X, and let y1 up to yn or yeah, in C be arbitrary. Assume, that's important, assume we can interpolate. Assume there is G in H that interpolates these points. Then the projection of G is the unique function of minimum norm that interpolates this point. Proof. First, some part is already shown, the part that interpolates, because we already saw that PFG at point x1 is equal to G at point x1, and this is y1, up to xn. So we have interpolation. PFG interpolates. And why is it unique? In a sense, it can be described at of the minimum norm. For any other edge, it's written here. Well, suppose G1 and G2 interpolates, both of them. What can we say? Then consider edge equal to G1 minus G2. So h of x1 is equal to g of x1 minus g2 of x1. It's 1 y1 minus y1 equal to 0. And the same h of xn is equal to 0. H of x1 up to h of xn equal to 0, we saw that this is equivalent to say that h is orthogonal to h of f. This was mentioned somewhere above. Here it is. If a function is 0 at those points, it's equivalent to say that it's in the orthogonal space. So in other words, G1 can be written as G2 plus H, where H is in HF perp. This is also somehow reversible. So it means that if you start with, assume that H is in HF perp, and you define G to be G2 plus H, then clearly G2 interpolates. G interpolates. These points. Like in the linear differential equation or some other concept, we can present all the functions which interpolates. So the set of all these functions are this form. Any interpolating function is of the form one function which I choose to be Pf of G plus another one which is orthogonal to this space. I choose Pf of G because it's in this space. And all the functions have this form. A complete characterization of them. And you see that the norm now, because of this orthogonality, so this is the norm of Pf of G squared plus the norm of H squared. So this is minimal. If and only if H is equal to 0, which means that F is equal to Pf of G. That's the only function in this space which gives you the minimal one. There is another indirect message also in the proof. I mean, it is mentioned, but I want to clarify it further. If you have G1 and G2, which both interpolates, both interpolate, then uniqueness tells us that the projection of G1 is the same as the projection of G2. At the end of the day, you end up with the same function. And this function is in the span of kx1 up to kxn. Please let me repeat. This proposition does not say that we have all the time an interpolation. It says that, look, there was an assumption. It says that if the interpolation is possible, it's part of assumption, then there is a unique one of the minimal norm, which is a linear combination of kx1 up to kxn. True? So therefore, that is good. We know that if there is any interpolation, we can go down and obtain something which is optimal of smallest norm, smallest energy. But on the other hand, still we do not know when is this possible. And that's the topic of our next week, to characterize cases in which interpolation is possible. And mixing with this, we will have existence and uniqueness theorem. Up to here is just the uniqueness. Existence is for the next week. Thank you very much. I think it's enough for this week.